Okay, in this video, we're just going to talk about continuous versus discontinuous because this idea is actually really important when we start to talk about especially things like our limits. So let's talk about what continuous means. Now, there is a big formal definition of what continuous means, but we're just going to give a very little simple explanation that will probably be good enough for us to understand right now about what continuous means. Later on, when you get to calculus, they'll have a big formal thing about what it is and all of that. So, but for right now, when we talk about continuous, we're talking about a function. So a continuous function, right, is one that that has no breaks in it, I guess you could say. And sometimes I think about it as you could write it with one pencil swoop. So without picking up your pencil. So if I can draw the whole function without picking up my pencil, then it's continuous. Now, some people think continuous means that it goes on forever on both ends, but there's lots of functions that go on forever on both ends that are not continuous. So something like this function, right, this is going to go on forever and ever and ever in both directions, like this way and this way and this way and this way in all directions. But this is not continuous because I could not draw it with one big pencil swoop. So this one would be not. But this one, or another way to say not, would be discontinuous, right? But this one, however, if it's something like, so something that looks maybe like our cubic function, this would be continuous because I just drew it with one nice pencil mark. I didn't have to pick up my pen, I guess in this case, at all to draw the function. So continuous means I can draw it with one big pencil mark. Now the thing is, there starts to be like a question about something like this function where it has an endpoint and there's no graph over here. So is this function continuous? So we like to call this one, so this would be something like our square root function that, doesn't have any negatives over here. Sometimes we think about this one, we would say that this one is continuous everywhere within the domain. Or everywhere the domain is defined, so maybe, So if you had, y is equal to the square root of x, well, obviously the kinds of numbers that I can't put in here would be, -1, -2, -3. Now, the only thing is I guess there is one place where the domain is defined that it probably wouldn't be considered continuous, which would be right here at the endpoint. Because one thing for continuity is that, you have to have something on both sides. So in this case, I guess it wouldn't be continuous here at 0. So not quite everywhere that the domain is defined. But for this whole piece of the function, so basically this function, oftentimes we consider it as continuous because it's continuous everywhere except for, that one point. Yeah, it's not continuous over here, but there's no function over there. So, the part that we know of as the function is continuous. So this leads us to another idea where, you can be a continuous function like something like this, or you can be continuous only in some places. So this function would be continuous from, like if I was here at 2 to 7, right? On this interval, you can be continuous over an interval. So this function would be continuous over the interval from 2 to 7. Or you could pick a ton of different intervals where this would be continuous. But it obviously would be discontinuous from like -2 to 2. From -2 to 2, it's discontinuous. There is discontinuity in there. Okay, so you can be continuous over an interval, over a very specific amount of space. You can be a continuous function, meaning I could draw the whole thing without picking up my pencil. Okay, so before we talk about the discontinuity in a second, we're going to talk about a couple of different kinds of discontinuity, but let's just talk about continuous for a second. Let's think about some graphs that would be continuous. And we kind of know a lot of those. So something like y is equal to x. Well, what is that a picture of? It's a picture of a line, right? Things like linear functions are continuous because, well, there's no domain restriction, right? A domain restriction will be something that would cause it to be discontinuous, just like this one. This one has a domain restriction. So that's why, you know, talking about continuity gets a little bit trickier, because there's a place where, yeah, it's not continuous here because over here, I just start and then I go. There's no function over here. But here, like if I go to the left and to the right of every single point, there's another point that's sitting right next to me. Okay, so that's another way you can think about it. You know, there's always a point sitting right next to me on both sides. But this one, when I'm here, there's nobody over here, but there's somebody over here. But here, there's somebody next to me on either side. And the same thing here. Okay, they're right next to me on either side. So, you know, linear functions. Well, linear functions fall in a category of functions called polynomials, right? Polynomials. So anything that falls in these categories, you know, of a polynomial, well, these things don't have domain restrictions. And we know that they don't have endpoints. They don't have any problems. They're always just going to be nice, cute curves that go on forever and ever, right? And so all of these functions, all polynomials, are continuous. I don't know why I can't spell continuous. Polynomials are always continuous. So if you're in the polynomial family, you're always continuous. So that's an easy one, right? Let's just take a look at a couple of other functions so that we kind of learn a lot about. So something like an absolute value function. So something like this, would that be a continuous or a discontinuous function? Well, he looks like this, doesn't he? So this guy, he has a nice sharp turn here. He's not smooth curves like our polynomial, but he's still continuous. I could draw it with one big pencil swoop, so that would be continuous. And later on, you're going to find out that these little pointy places, those are called cusps, just to add a little extra. That is a weird thing when we're talking about calculus. You'll talk about those more, but it's continuous. Okay, so what ones wouldn't be? Well, which ones have domain restrictions? Something like 1 over x, which was sort of like this guy that we saw on the other side of the page, right? 1 over x would be a function that's discontinuous. But usually these are discontinuous at a particular moment in time. They're not discontinuous in a bunch of different places. Something like our step function, right? Those would be discontinuous functions. They're things that look like this, right? That's discontinuous. Even something like this. Let's say x plus 1 over x plus 1. We'll do x plus 2. So what does this function look like? This is a rational function, but when you cancel these out, it's actually his twin, right? So there's a hole here. So his twin, like if you were looking at somebody that looked just like him, except for this hole, it would be this. So this is actually like a line with a hole. So it's 1, 2. It's this line. There's going to be a hole where x is equal to -1. So over here at -1, I guess that would be here. This is what he's a picture of. This one's actually discontinuous. There's a moment of time where, you know, I had to pick up my pencil to get over that hole. But everywhere else, he's continuous. Okay, so it's not a difficult idea, but I don't know, for some reason, it kind of makes people feel nervous to decide whether it's continuous or discontinuous. So that brings me to the one more thing I wanted to say while we were talking about this. There's different kinds of discontinuity. So one type of discontinuity would be this kind. And we call that non-removable. Non-removable discontinuity. So this one, the only way to draw this graph is this way. And I think it's actually easier to talk about this one first. So let's look at this one. This one is called removable. Removable discontinuity. Now, if you take a look, this function and this function are kind of the same function. They're almost the same. They're the same at every single place except for x is equal to -1. All the other outputs are identical. They are the same, essentially the same, right? The only time when you would have a problem is if you happen to be standing right at -1. X is equal to -1. But otherwise, you could basically say they're the same. right? So this one would be a removable discontinuity because it's very easy to just ignore that little hole and fill him in, and make this function look like this function. So if you can draw the picture without the discontinuity and it looks like the same picture, then it's removable. So you see how if I just plugged the hole, like they're basically the same idea. Everywhere else they're the same. So everywhere else my pencil would be doing the same thing except at that discontinuity. However, this one, in order to remove the discontinuity, I would actually have to draw a whole different picture, right? Because this one is creating some kind of asymptotic thing. You're having an asymptote there. It's going up forever. It's going down forever. So in order to get rid of this break in the graph, it would mean that I'd essentially have to change the nature of who he is, right? He doesn't have a twin that doesn't have discontinuity. In order for this graph to have no discontinuity, he'd have to change who he was completely, right? It's not just like putting a little, makeup on your little hole. This one would be like, I have to change completely who I am as a person to be non-discontinuous or continuous, right? So non-removable and removable discontinuity are two things that you'll be talking about a lot about. So that's the idea of those. And I think that's pretty much all you kind of really need to know for your foundation here to be able to move forward in this section. So hopefully that was helpful, and you learned something that you didn't know before.